Let us now study about the resolving power of a telescope. Before understanding resolving power of telescope, let us define a term called as limit of resolution. To define this, we can say that the limit of resolution of a telescope is the least angle that the two objects have to subtend at the eye so that they are just resolved. That is, if as seen here, if there are two faraway objects, say like two stars, let us call them as S1. Let's call the stars as S1 and then S2. So somewhere here, use an optical instrument like a telescope. I'm just drawing one lens for it, but it's a telescope, and eye is very close to the telescope. So some books will write this as eye, and some books will write this as the instrument. Both are interchangeable because the human eye is very close to the optical instrument. So this angle here d theta is called as limit of resolution, but it is called as limit of resolution provided two objects are seen as two distinct objects, or technically we say they are just resolved. So the limit of resolution of telescope is the least angle that two objects have to subtend at the eye so that they are just resolved. Make sense out of it. Let's take a case where we have an optical instrument, say telescope in this case, and then imagine light coming from a very far away source. Let us take only one source. Example, think far away star. In this case, since light falls on this lens, light would diffract. Actually, what we get here is not a single spot, because from ray optics we studied that you will get a single spot, but because of diffraction and also because of the aberrations in the lenses, like spherical aberrations, rather what we get is a finite spot as shown here. So somewhere here, if you have a screen or an optical instrument, we get a finite spot like this. Along with it, we get even darken and bright bands also. We get a band of this kind, but these would have less intensity because around 84% of the intensity would be in this region only. So we don't get a point object here, rather we get something of pattern like this, where you get a bright spot, and also we get a pattern here of which the bright spot would have maximum intensity. Recall that in case of diffraction, the central maximum have the highest intensity. Case of here, this would have around 84% of intensity. So this will have some radius that's called as R0. So R0 is the radius of the spot. From ray optics, it should be a finite spot which is very small, but because of diffraction, as we discussed earlier, it will be a bright spot like this. And this radius is given by 1.22 lambda into f by 2a. Now this has not been proved because the proof of this beyond the scope of the syllabus is not proved here, but we can understand what the terms are. The lambda is the wavelength of this light falling on the lens, and 2 here the diameter of this lens. Some books write as just a only, observe it, but basically what comes in the denominator, basically diameter of this telescope, and f would be the distance between the focal length and the screen or human eye. What is f? This is the pattern what we get here. Now instead of one source, if you have two sources as given here, then what happens is, if we redraw the diagram, then a screen somewhere here, there are two sources, then what happens is each source will have its own pattern. If you observe carefully here, if you draw the intensity pattern for it, then this would be like minimum, like this, as seen here. This will look much better. So we get the minimum and maximum, we get a pattern of this kind. What we get, this would be the edges of the circle, a circle of this kind, what we get. And then here you get a pattern here. So on the screen we get two patterns, pattern because of say one object, the pattern because of the other object, like this. In this case, when the centers of both the patterns are far away, for example, think the star S1 somewhere here and S2 somewhere here, keep in mind that they're very very far away. For sake of understanding, are drawn closer, but they're very far away. Then each will have its own pattern. The idea here is we won't get point objects, rather we get a pattern as seen here. So this would be the pattern because of S1, and this would be the pattern because of S2. Each of it will have its own pattern. In this case, it is very obvious that S1 and S2 are seen as two different objects. Now, there are three cases here. Case where the center of one and this is the center of the first say source, and somewhere here it's like this, that is center of second also coincides somewhere here. In this case, the centers are not clearly distinguishable. This is said to be not resolved. Instead of this, if you have a case where the minima of one falls on the maximum of other, that is something of this kind, that is if the minima, read out this, you have one pattern like this, and then the center of the somewhere here, and this its first minima. If the minima of one falls on the maximum of the other one, in this case these are said to be just resolved. So just resolved means that the minima, that is the dark band or minima of one pattern or due to one source, if it falls on maximum of other, then it is said to be just resolved. Now here the maxima of one pattern, let us call this as due to star S1, this due to star S2, same here due to star S1 and S2. Now the maxima of one falls within the maximum of other. This is the entire range of it. It falls within that range. In that case, it is not resolved. Now suppose we'll take a general case where the minima, the maxima are so far away that you can clearly see them as two different objects. This is called as well resolved, which means here we can see them as two clearly different objects. In case of just resolved, we can see them as two different objects, are just able to see it. Diagram here will make it more clear. As seen here, you can draw in terms of the pattern also. In this case, observe carefully, these two objects, the centers of the two objects or the center patterns of both will coincide. This is unresolved or not resolved. Here you can see they're just able to separate it, which means this implies a case where the maxima of one falls on the minimum of other. It is said to be just resolved. While here, in case of unresolved, we can say the maxima of one falls within the minima of other, somewhere like this, falls within the minima of other. Make it more clear. So bigger one. This is the maxima, and then here just next to it we have one more, like the maxima are almost close to each other, not falling on minima. This is not resolved, unresolved. Rather here they're very far away, like this. This is the intensity pattern. So this is said to be fully resolved. Now coming back to the discussion what we had earlier, we want to define what is limit of resolution. So it is defined as saying the least angle that the two objects have to subtend at the eye so that they are just resolved. Means in this case the angle made by the two objects with the eye, the angle made in this case is called as d theta. It's called as limit of resolution. And the d theta, when you solve this pattern, you know what is r naught, and from here you can find what is d theta. We call that r naught was given as 1.22 lambda by 2a into f. The angle here is called as d theta. It's called as d theta. They are just resolved. Now the distance between this and this would be the focal length, and want to find the separation. Then if they are just resolved, this becomes r naught. That is, think of a case where the centers are just resolved like this. Then this distance between them, it becomes 2 times r naught. This is well resolved, but rather what you want is you want a case where centers are something like this. So this is just resolved. Distance between this to this would be r naught. This is not resolved. This is just resolved. This is well resolved. In that case, the distance between center to center becomes r naught. So putting that here, what we get is we can say this r naught means r naught into d theta would be equal to, rather it's not r naught into d, it's like this, r naught bf into d theta, because recall the arc length is equal to radius into the angle made. That's been used here. This is the arc length in this case. So comparing these two, we can say that 1.22 lambda into f by 2a is equal to into d theta. From this f gets cancelled. Therefore, the limit of resolution which we learnt as d theta is equal to 1.2 lambda by 2a. This is the form for limit of resolution. From here, we'll define a very important term called as resolving power, which was defined earlier also, but we'll just define once more. Now it is defined as the reciprocal of the least angle subtended, because here we learned d theta is equal to 1.22 lambda by 2a, and this angle is measured in terms of radians because we're using the concept of arc length. D theta is equal to 1.22 lambda by 2a. We can define resolving power using d theta also. So in this term, resolving power be equal to reciprocal of limit of resolution. You can define saying that it is the reciprocal of the least angle, because d theta was the least angle for which the two objects appear to be just resolved. The reciprocal is called as resolving power. From here, to write it, resolving power is equal to 2a by 1.22 into lambda. This would be per radian, because d theta was in radian. Now the question is how to improve the resolving power. Now, if you recall the formula, resolving power was, just go back and look at it, was 2a by 1.22 into lambda. From here, if you look at it, we can improve the resolving power by increasing this term and by decreasing this term. So we can say the resolving power of a telescope can be increased by increasing the diameter, because 2a is called as diameter of the telescope, objective telescope. So by increasing the diameter of the telescope, we can improve resolving power. And second way is to decrease the wavelength of light incident. So by adopting these two, we can have a better resolving power. But problem here is, if we increase the diameter of the objective, then aberrations will come into picture. That is, spherical aberrations as well as chromatic aberrations will come into play. There is a limit beyond which we can't improve the diameter of a given telescope.